हेलो चेक चेक देखो चेक 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 হ্যাঁ শোনা যাচ্ছে 1 2 3 হ্যালো হ্যালো 1 2 3 হ্যালো শোনা যাচ্ছে তোমার 1 2 3 হ্যালো হ্যালো চেক 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 হ্যালো হ্যালো একটু ল্যাগ আছে হ্যালো চেক
Good afternoon to one and all present here. It gives me immense pleasure to welcome you all to this distinguished gathering organized by the Indian Statistical Institute's Alumni Association. We are honored by the presence of eminent academicians, respected faculty members, alumni, and my dear fellow students. Before we begin, please allow me to introduce myself. I am Rupsha Rai, a student of MSTAT first year, and it is my privilege to anchor today's program. This occasion holds special significance for all of us as it brings together students, faculty members, and alumni on a shared platform to celebrate academic excellence, to strengthen our bonds with the alumni community, and to learn from some of our most distinguished alumni whose works have made a profound impact at the global level. Such gatherings remind us not only of the rich academic legacy of Indian Statistical Institute, but also of the diverse paths and opportunities it continues to open for all its students. Without further ado, may I now request our esteemed dignitaries to kindly take their seats on the dais. I would like to warmly welcome Professor Shashi Mohan Srivastav, Chairperson of ISI Alumni Association, Professor Bishwabroto Pradhan, Dean of Studies, Indian Statistical Institute, Professor Shudipto Banerjee, Department of Biostatistics, UCLA, USA, and our chief guest for today's program, and Professor Mohammad Zafar Anis, Secretary of the ISI Alumni Association. Thank you so much, sir. We now begin the program with the felicitation of our chief guest. It is truly a matter of pride for all of us to welcome Professor Shudipto Banerjee, an alumnus of ISI and currently a faculty member in the Department of Biostatistics at University of California, Los Angeles, USA. Professor Banerjee is widely recognized for his seminal contributions to Bayesian hierarchical modeling and spatial data analysis. His academic journey from ISI to leading in global institutions and his leadership roles continue to inspire students and researchers across disciplines. I now request Professor Bishwabroto Pradhan, our Dean of Studies, to kindly felicitate Professor Banerjee with a shawl. May I also request my senior, Ms. Shevonti Basu, MStat second year, to present a flower bouquet to Professor Banerjee. Thank you very much, sir. It is truly an honor for all of us to have you here with us. To formally commence today's proceedings, I now invite Professor Shashi Mohan Srivastav, Chairperson of the ISI Alumni Association, to deliver the welcome address.
It is a really great pleasure for me to welcome you all, and thank you for coming. My special thanks are reserved for Sudipto Banerjee. He was our student. Sorry, he's now a very distinguished biostatistician, very distinguished, and so I know he's very much pressed for the time. Immediately after this program, he will rush to the airport to catch a flight. Are you leaving the country also? He is leaving the country. So, thank you very much for accepting the invitation. And uh, the, I would like to read out few lines from the recommendation of the fourth review committee, the last review committee. So those of you who are not much aware of ISI, how ISI is governed, so essentially ISI is governed by ISI Act 1959, which was passed in the parliament when Pandit Jawaharlal Nehru was the president, and at that time ISI was given the status of Institute of National Importance and was given permission to start degrees and so on. And then started our, what is now world famous program, BStat, MStat program, of which one of the stars is sitting here. And I, uh, I want to read it out because it, only the portion uh, which concerns alumni, I was very, very impressed. By the way, I was at that time when this committee submitted the report. I was in the council. I was a member of the council, and the review committee was very kind enough to even have a meeting with me, one-to-one meeting with me. And a few lines that I want to read out is the following. Creating the alumni connect has several advantages. So why do we value, why should we value? I mean, it's so nicely put that I think it is worth reading it out here. First, so there are several advantages of having Alumni Connect. First, the storehouse of knowledge, experience, and goodwill existing with the alumni base often proves to be a good blessing for the institute. Second, since they are looking at the institute from outside and have the opportunity to compare it with other institutes, it its feedback is critical for course correction by the institute. Finally, I mean, this is everywhere it is followed. Finally, if the alumni are requested to fund a specific endeavor by the institute where the government funds are inadequate, the alumnus have been known to oblige in large measures. And I have been personally requested by the chairman of the council, present council. He knows that I am the chairman of ISI Alumni Association, and ISI is going to, or ISI Society is going to have a centenary year in 2031 to raise corpus funds, and which ISI is planning to celebrate in a big way. Now, another part is also important. The review committee feels that the institute should immediately set up an alumni cell. And so let me inform you all that very strictly speaking, ISI Alumni Association is not a part of ISI. Neither it is a cell of ISI. It was created, it was formed by individual efforts, and I still remember attending I was then very, very young faculty, and that meeting was chaired by J. Roy, Professor J. Roy, and various other senior people, and that is where this was formed, and it had nothing to do with ISI. And till today, it is really voluntary. Whatever happens voluntarily. And ISI is kind enough to allow us to use its infrastructure, and beyond that, we get no support from ISI. And by support, I mean manpower support to run our office. We can afford only one person to help us a week. So we are so short of money, and also it becomes a big problem to create the executive committee because we have to really persuade people, and people come forward. Still, it has done some. It is still in existence because of the love of ISI that our alumni. And this is where I welcome this suggestion very much, that if ISI alumni has to contribute to ISI cell should be formed. And I was present in the council meeting where this resolution was taken. Sorry, support to this recommendation was given. So the review committee feels that the institute should immediately set up an alumni cell and make an attempt to, one, create the entire database of alumni and their current status. Some database we have prepared, and it is purely by individual effort, and we have absolutely no staff support. I mean, we have very weak staff support. So this is far from satisfactory. And there is one more thing that I would like to say here. Well, I was very much instrumental in making, this database Bitwitcher, and because I am an academician, I have no reach to industry, and also I don't know how to get information about people working in industry. And I have told many of my executive committee members that we should do something so that we also have a database for people working in industry, and there are many and many successful ones. Second, reach out to alumni on a regular basis and keep them intimated about the development in the institute and making them stakeholders in the institute. And following this, I did inform alumni of some of the current developments that is going on and which is worrying many of us. Take the help of the experts from the alumni base on many matters, e.g., course development and curriculum development. Of course, this is a call of ISI. ISI cannot do anything about it. Then seek their suggestions about ways to improve the institute functioning. Again, the ball is in the court of the institute. Seek their help in generation of corpus fund and in times of crisis. Well, some effort has been made by ISIAA, and we have received uh, some fund, not too big, but still some fund we have got. But this cannot go on just as a voluntary service. ISI, most of the institute, even places where I have worked abroad, I mean, this is an official thing which is done. IITs and such, there are sales which where institute supports a lot, and that is needed. Highlight the achievements of the alumni and celebrate it. Well, we are on the way. We have started it, as you can see. Routinely invite alumni leaders for lectures, session, policy planning, and for co-investigation of important research and application problems. So, ISI alumni, as we all know, I mean, it's as rich as for uh, any institute in the country, and we are very very proud of them. And if ISI can act on this thing, I think it will be very very beneficial. And with this, I once again thank you all for coming. And
Thank you so much, sir, for sharing your thoughtful perspective and stressing on the importance of our alumni community. Next, I would like to invite Professor Bishwabroto Pradhan, our Dean of Studies, Indian Statistical Institute, to address the gathering.
Good afternoon, everyone. It's a really pleasure for me to welcome you to this Alumni Day celebration. I am also an alumnus of this prestigious institute. So, being an alumnus of this institute and addressing the distinguished alumni, that's really pleasure for me. So this Alumni Day celebration is basically an opportunity to reconnect with everyone. And so what I can understand that many participants are there online, right? And this opportunity really gives us to reconnect with everyone, and we need your these suggestions, help actually for the institute, for our alma mater. Actually, I would like to emphasize one thing that ISI is at the crucial juncture. I would say uh, possibly that ISI will be reshaped basically. So the process is going on. So the institute, what we have seen actually, may not remain same. So at this crucial juncture, actually, we need your inputs. And I would say that it is the time to give back actually. It may be through, mentorship, this helping student needs, maybe developing facilities and all kind of things. Because you know that our distinguished alumni have established nationally, internationally in different sphere of life. There, this input would greatly help us actually. And I thank this ISIAA, this the executive committee actually for organizing such a wonderful event. Yeah, would have expected more participation. So I would request see how this participation can be enhanced. I mean, more and more participations, and also this maybe more programs under this ISIA. As Professor Srivastav mentioned, actually, we need your help, whether it is, this for instituting new program or this input for, say, whatever that syllabus review, restructuring any program and all these things. As I mentioned that our alumni are working in many, whether it is in academia or industry, so that help would be required. And today we have Professor Sudipto Banerjee actually who will be delivering the talk. So we are really grateful to you. And so once again, I thank all the participants here.
Thank you, Professor, for your inspiring words and for enriching today's session with your thoughts and perspective. Next, uh, next we move on to a segment that keeps us connected as the part of the larger ISI family. I invite Professor Mohammad Zafar Anis, Secretary of the ISI Alumni Association, to share updates of the activities of the Alumni Association and to highlight the achievements of ISI alumni over the past year.
Good afternoon to all of you. Today is Alumni Day, which we celebrate. It's not an annual general meeting where I should go through all the updates of what we have been doing during the past year. But suffice it to say that the organization is active. We are in the process of doing things which are legally correct, in the sense that our income tax returns, our registration process are intact. I'll just read out a few of the good achievements of our alumni. This list is necessarily small and incomplete, partly because we don't have all the information, and the information that we have here is also restricted to largely academic work, those who are in the academia, and that too also in the subset of mathematics and statistics. But nonetheless, it feels happy and good to celebrate what some of our alumni have achieved during the past year. So the names are, this list is by no means shall we say, in order of merit or something of that sort. It's just a random order. Number one, Professor Saurav Chatterjee of Stanford was elected as a member of the American Academy of Arts and Sciences. Professor Bharmar Mukherjee was a keynote speaker at the 65th World Statistics Congress organized by the International Statistical Institute. She was also elected as a fellow of the ISI, International Statistical Institute, and a fellow of the Institute of Mathematical Statistics. Professor Shomik Pal was elected a fellow of the Institute of Mathematical Statistics for his outstanding contributions in optimal transportation problems. Professor Sujit Ghosh at North Carolina, he was awarded the Weber Fellowship by the Department of Science and Technology of the Government of India, and he is being hosted at IIT Bombay by Dr. Radha Srivastava, who is also an alumnus of ours. Professor Deepak De, well-known name to us, received the Lifetime Achievement Award of the Indian Bayesian Society. Professor Shushmita Mitra was elected as a Fellow of the Indian Academy of Sciences. Professor Shushmita Shurkole was elected as a Fellow of the Indian National Science Academy. Professor Neena Gupta, our colleague in the StatMath unit in Calcutta, was awarded the prestigious J.C. Bose grant by the Government of India, and she also delivered the Emmy Noether Lecture this year. Professor Souvik Roy was awarded the Mahalanobis Memorial Medal by the Indian Econometric Society. Professor Molanath Banerjee, he has been serving as the editor of the Statistical Science, which is a publication of the Indian Institute of Mathematical Statistics, and this position is up to the end of this year. Our colleague Kiranmoy Das, who also happens to be the Assistant Secretary of this organization, received the ISI Early Career Award in Statistics and Data Science. Professor Arnab Laha has been appointed as the first RBI Chair Professor at ISI Calcutta. Tamajit Sadhu Khan, a research scholar in the StatMath unit, received the International Mathematical Unit Breakout Graduate Fellowship. Snehin Sen of the MStat program secured the first position in the CSIR UGC net, scoring a perfect 200 out of 200. Sinchan Snigdha Adhikari, he was an alumnus, secured the first rank in the ISS examination. And I'll end by going to the industry. Prabal Datta, who happens to be my batchmate in BStat and MStat, was conferred the Knight's Cross of the Order of Merit of Hungary in recognition of his work in developing and implementing the digital transformation of the Hungarian service sector and his role in supporting those living in difficult circumstances. He is presently serves as the Vice President and Managing Director of the Eastern Europe section of the Tata Consulting Services. We are proud of their achievements and also those of others whom we could not, whose names are not available with me. I would encourage people to respond and let the Alumni Association by emailing the achievements of our colleagues so that this is recorded and reflected in the annual general meeting. Thank you.
Thank you so much, Professor, for that comprehensive overview and for showcasing the remarkable achievements of our alumni, which continue to inspire us and strengthen the ISI community. I now request Professor Kiranmoy Das, Joint Secretary of the ISI Alumni Association, to propose the vote of thanks.
Good afternoon, everyone. It's really an honor for me to be a part of this wonderful event this afternoon. On behalf of ISI Alumni Association, I would like to extend my heartfelt gratitude to our esteemed guest, Professor Sudipta Banerjee, Director of the Institute, Dean of Studies, and all executive committee members of ISI Alumni Association for their assistance in various capacities. Sincere thanks to Dean's Office, Director's Office, Estate Office, CSSC, Audiovisual Unit, RIPRO Unit, Electrical Maintenance Unit, and ISRO Office for their kind support. Special thanks to 2003-2005 MStat batch, the sponsor of High Tea this evening. I thank my younger colleague, Dr. Suman Majumdar, who will be chairing the next part of the program, that is the academic talk. Thanks to our student Rup Share for her wonderful stage anchoring, and I thank the performers of the cultural program to be held right after this talk in advance. Finally, thank you all present here for making this event a grand success. Thank you one and all. Thank you.
Thank you, Professor, for those gracious and heartfelt words of appreciation. We now move on to the next part of today's program. It is my pleasure to invite Dr. Shumon Majumdar, Assistant Professor at Interdisciplinary Statistical Research Unit, ISI Kolkata, to the stage. Dr. Majumdar will introduce our chief guest and take us forward to the talk with Professor Sudipta Banerjee. With this, I hand over the session to Dr. Shumon Mojumdar. Thank you, everyone. I hope you enjoy the talk.
Hello.
Thank you for waiting. Thank you, Rupsa, for wonderful handling of the event so far. Up next, we have the talk from our chief guest, Dr. Sudipta Banerjee. Dr. Banerjee has been an alumni of this institute. He received his MStat degree in 1996 and went on to obtain a PhD degree in statistics from the University of Connecticut in 2000, after which he joined the Department of Biostatistics in the University of Minnesota, Twin Cities. And after 14 years there, he moved on to Los Angeles to join as the chair of the Department of Biostatistics at the University of California, Los Angeles. And he's currently the senior associate dean there since 2023. He is an elected fellow of the American Statistical Association, the International Mathematical Society, uh, the American Association for the Advancement of Sciences, and the International Society for Bayesian Analysis, of which he was the president in 2022. He has won multiple awards, including the George Snedeker Award and the Jerome Snack Award recently. He wrote 3 books and he has authored over 200 research articles. His primary research involves Bayesian hierarchical modeling and spatial data analysis with applications in geostatistics, public health, and epidemiology, to name a few. His recent interest has been in scalable models and also incorporating machine learning and AI models into the Bayesian framework, which is the topic of today's talk. So please welcome Dr. Sudipta Banerjee.
Good afternoon. Oh, okay, sure. Thank you. Can you hear me, everyone? Thank you so much. Good afternoon, and thank you so much for being here. I don't know, words fail me. I think this is a massive honor for me to be recognized by the Indian Statistical Institute. I was a student for 2 years here as an MStat from 1994 to 1996. And every day that I was here, I always felt that I was probably not in the right place because there were so many remarkably gifted people around. And I was only trying to learn and figure out my way. And I think, I was a decently good student, but I was by no stretch of imagination an extraordinary student here. But I was always welcomed. And when I talked to my professors and to my colleagues, I think there was this beautiful learning environment where we were trying to learn, and we all had our own journey, and we were always felt, welcomed and supported. In particular, I would like to first of all thank Professor Srivastava for his very gracious invitation to me to be speaking here. Professor Srivastava himself, although I did not take a course from him, has had an influence and impact on me because he helped me actually with some group theory problems and guided me on what to read and how to understand mathematics. I was not someone, as I said, who was some of the customarily mathematically gifted students that this institute admits. But as again, it was just the most positive and wonderful experience that I've had here. And the training I received here stood me in good stead throughout my career. And during my research, as well as whatever I have absorbed and learned on the way, and as I continue to do so, I always go back and figure out the importance of the foundations that I received here in the Indian Statistical Institute, particularly with regard to mathematical formalism, which is very, very important. Even if you're an applied statistician, or if you're a computational statistician, or if you're a machine learner, or if you're a data scientist, whatever you call yourself nowadays, foundations of and the rigor of mathematical thinking and presentation becomes very, very important. Otherwise, we won't be able to write well. Otherwise, we won't be able to understand the papers that are deeper and that are more abstract. And I think the Indian Statistical Institute has played a very profound role in my own journey in that regard, for which I will always be deeply, deeply appreciative. I also have so many of my professors here in the audience. It's a great honor to see them here. And there's Pradiptada, there's Parthada, there's Amitadi, there's Professor Raha. I have seniors like Goshalda here, who's actually a dear friend also, and I've learned and absorbed much from actually his work as well. So truly massive, massive honor. Friend Dibuda, Lahada, so thank you so much for making time and listening to me. So I'm going to move forward and get to my talk. As Professor Srivastava mentioned, otherwise I'll miss my flight. I have actually given this kind of talk over the last year or so, particularly because I have discovered sort of a role for myself and my team in research in machine learning. I was always kind of a little confused where I stood there. By the way, Amitadi is here, and my first course in machine learning was actually taken from her in the Indian Statistical Institute here. So, that also was part of my foundational training here. But typically, in machine learning conferences, I've discovered that they first present the results, and then they actually go to some of the underlying algorithms and theory. But here, these are hallowed grounds in statistics. This is one of the most esteemed institutes on statistical training, statistics. So therefore, I've actually modified this course, or rather this talk, to be presented in a manner that I will focus upon the statistics a little more than usual. And I'm going to bring the artificial intelligence part and the machine learning part a little bit later. So how they can actually get together. So the main actors or the main topics here are spatial statistics, what it is, I will explain a little bit. And then there is this new technology that has actually invaded our sphere, which is wearable devices. So wearable devices are like your, Fitbit or phones that you carry with yourself, and you measure perhaps the number of steps that you have or a lot of other things. And that leads us to a very interesting topic in stochastic processes and spatial processes, which is basically how to construct spatial processes for trajectories. And I'll explain what that is. And then comes artificial intelligence. And in particular, artificial intelligence is already a very broad word, and many folks interpret it according to their own sort of research and how they interact with AI. I'm going to be focusing on Bayesian transfer learning. And then the case study will be on this emerging field of spatial energetics, which is basically data from wearable devices. It's a fancy word that is taking some traction, or getting some traction in the United States, but it basically is about analyzing data from wearable devices and mobile health data in particular. So that's how this will connect together, hopefully. So I'm going to start a little bit with what is spatial statistics, because of course many of you probably know what it is, but if I don't connect it, I won't be able to go forward. So it will be important to understand what the traditional role of spatial statistics is in the world of statistical inference, and then how we are going to take it forward into these wearable devices and so on. So what is spatial data? When we think about space-time, we often tend to think about physics, and we tend to think about astrophysics and so on. But at a very fundamental level, when we are looking at data, it is basically spatial data. We, broadly speaking, describe it as data that carry geographic information. So that means it's actually collected over locations or points. So for example, in climate science, if you have weather data, you're looking at temperature, precipitation, air pressure at every location over the entire Earth. Okay, very high resolution data are now available freely. Does not matter where you are, you don't have to pay for them. They're all from satellite data, and they're pretty high resolution. So you have something like that. Forestry, in India, of course, there is a lot of activity in forestry, and there is a lot of activity in forestry across the world. There's been a renewed interest in forestry, particularly for the health of the planet. And here the data include, for example, amount of biomass and so on, certain gases that may have been measured based upon the number of trees in little pixels across a country or across a region. Ecology, where people study the extinction of species, or the population of species, or or how they flourish, or how they are becoming extinct, and so on. So again, there is location. Okay, what type of species exists where? So the where and the why is about space-time data. Environmental health, this is a daily thing. I mean, during COVID as well, you saw, for example, where are the cases coming up, right? Where is it actually rapidly increasing? How is it spreading? Disease epidemiology, basically what regions in the country or in a state are actually seeing high incidences of certain diseases and maybe less so in others. In economics, you have real estate marketing. Can I actually look at a particular neighborhood that is actually developing and then try to see how the prices of the homes in those neighborhoods are going to look like, and forecast it perhaps as we do in time series, but taking into account where the homes are. So there are a lot of attributes of these data. Very typically, you have a lot of important predictors and response variables. They are often presented as maps. And then, of course, this data nowadays, big data, it streams over time. So you have a lot of data coming in. And then there are other examples where spatial need not refer to space or necessarily on Earth. So for example, neuroimaging data for each voxel in the brain, genetics. I've actually followed Professor Parthuti Majumdar's work, and there's this position along a chromosome, and there's an area in spatial statistics. I don't work in that area as much, where they basically try to understand how to model that proximity. And so there's a lot of different varieties of trying to understand spatial dependence, which basically means that if I am close to you, then I'm more like you. That's the basic role and how we actually look at it. Let me give you one quick example. This is a map of the continental United States. On the left-hand side, what you see is a map where you basically try to look at the biomass. So that is actually biomass. I'm not going to go into the details here, but it's like a collection of gases. And essentially what we do is we look at biomass emission as tied to trees. So as I said, forestry was an example where spatial statistics has played a very important role, and particularly for the health of the climate, and we want to actually try to understand it, its behavior and how it disperses and so on. So you can look at forest biomass aggregated between 1999 and 2006 at about 114,000 plus plots, spatial locations. And this is basically just plotted, and there's no modeling, no statistics, just the point and the amount of biomass at a particular scale has been plotted. Red means there is less biomass, and blue means there is a fair bit of biomass. On the right hand side of the map, you see a map that has been constructed from what is called satellite imagery, and it actually represents normalized difference vegetation index, which very simply put is the amount of greenness that you can actually see from space on a particular region. So if you look at these two maps, without getting into any formal statistics or formulation, you can at least see that where there is a little bit of blue here in the northeast, for example, let me see if I can use the pointer, right here, you see this blue, there is more green, okay? Then again, the blue stretch here in the Pacific Northwest, you have a stretch of green here. And then this is the arid part of the United States, a lot of desert and Arizona and so on, and you have you have less biomass here. So without even doing any formal statistical modeling, you can understand that there is kind of an inverse relationship between these two, which is quite understandable because greenness essentially is correlated to amounts of forest, and if there's more forest, there is more biomass. So that's how it actually goes. The first thing that statisticians tend to do when you have data like this is to basically say, well, I'm going to model biomass and I'm going to take NDVI as a regressor or a predictor. Because NDVI is available at a very high resolution, whereas biomass is typically still calculated based on census data. That means people go, field measurements are taken, and that's how it is reported. So if you have NDVI, you can look at regress, learn about the relationship, and then you will be able to predict biomass with NDVI at any arbitrary location. That's the problem of spatial prediction. If I just fit this model, which is a simple linear regression model, I can do that. And then if I actually look at the map of the residuals from the linear regression model, meaning, adjusting for the least squares estimates, I just take the residual error. Then I basically get the map on the left, and you again see a fair bit of clustering, a fair bit of little blues here and a fair bit of little reds here that are still clustering. The formal way to actually try to understand what other information is available in this residual, when particularly you are interested in spatial dependence, is to calculate what is called a variogram. So from the 1940s to almost the 1980s, there's been a ton of papers, like hundreds and hundreds of papers, that have come on how to construct a variogram, what the stochastic process underlying the variogram is like, how the stochastic process's property, like stationarity, non-stationarity, affects the variogram, and how the variogram is in fact estimated from data. But we moved on because we have developed, likelihood-based inference, and we have developed Bayesian models and so on. So we don't really work with the variogram estimation as much, we do much more. But it is still a very important exploratory data tool, because when you feed the variogram, when you feed these residual errors rather into a variogram function, then what it does is it typically looks at the squared difference between the value of the residual at a location S and a location that is slightly displaced, S plus H. Okay, so what the the tendency is that, as I said, the first law of geography basically says that if you are close to me, you are like me. So that means if this h is really small, then you would expect that value to be really, small, right? Because they will be more like similar to each other. But interestingly, as h becomes larger and larger, what happens is the value, the difference between these two, which is like an Euclidean distance between the two, they basically become larger. Very simple concept, and what you do in practice, from the data comes in, you bin them just like you do any kind of numerical analysis, and then you average them and you get a plot. This is like an empirical plot. And as you can see, the smaller values tend to be at the smaller distances, and then as you actually go higher and higher, then it increases, the variogram increases, and beyond a certain point, of course, you're looking at a finite domain here. There's not enough data, so it flattens out and stays there. So intrinsically stationary process, stochastic process, and now we are getting into formal probability. If you actually take a realization of that, a spatial process, and you pass it through a variogram, and if it is a stationary process that has generated that data, then this is a very picture that you will tend to see. And there are three parameters, so to speak, that actually come out of this. And I have indicated them with the three straight lines, two horizontal lines and one vertical line. The lower line right here is actually what is called the nugget. That represents the variance of the residual out here. Okay, that's just like your ordinary least squares residual, take the variance. Okay, and then the top line here is the total variability. And then this vertical line, you see, is basically the distance beyond which you don't get to see much dependence. And you can prove this actually with essentially take the expectation of ys plus h minus ys whole square, make a couple of little assumptions on ergodicity of the stochastic process, and then you basically see that the variogram is essentially like an inverse of a covariance function. So the covariance function starts at 1 and drops down, whereas the variogram starts at a small value and increases and flattens. Okay, so that's basically the idea. What I want to focus on is that in that data, for example, what we see here is that a simple linear regression is not going to be enough because there is a lot of structure that is still there in the residual. And the role of spatial statistics is to try to understand that dependence and try to come up with a better predictive model. It's all about prediction in the end, which is why spatial statistics is very related to machine learning in many ways. So what we do, and there are lots of great books that have been written on geostatistical models. Noel Crecy's 1993 and Michael Stein's 1999 are two very, very good books, differently flavored. This is more on modeling. Stein's is much more on the theoretical side with formal asymptotics. But basically, like all good statisticians, one of the things we understand is, all right, well, instead of just having the noise, in addition to the regressor, I'm going to put in a spatial random effect here, or a spatial process. The question is, how am I going to actually model this spatial process? All right. So because one very important thing to understand is that I want to do inference on essentially an uncountable set. Not a finite set, not a countable set, but an uncountable set. What do I mean by that? Is that, well, look, once the model has been trained, your client is going to come to you with any arbitrary location, and you will be asked to predict the response right here at L. Okay, now one important point here, for those of you here in ISI, you will probably have noticed this. This is a white noise process, and as you know, white noise processes have weird things about, for example, not being integrable, and Borel measurability can become questionable. So when this particular quantity, the noise part, essentially does not necessarily bring this into a stochastic process. But on a finite realization, when you have data, then that is totally fine because, for example, this could be a normal distribution with IID normal over a finite set of points, and you have no problem, you have a valid likelihood, and you can actually estimate. But the spatial process is what is really our interest, and the most common way to actually specify this is using a Gaussian process, which basically means, when I teach this to applied statisticians, the way I like to put this is, Well, when you have a distribution, a probability distribution, that is for a random variable. But when you actually have let's say a random function, you don't know a function, well, then you use a stochastic process to model uncertainty. Okay. And so in some sense, you could look upon this as an unknown function of the locations, and you could assign the Gaussian process as an unknown, as a probability law on an unknown function. Or you could actually say, well, I'm going to split the error that I saw in the previous slide on the regression and split it up into structure and non-structure. Both mathematically they are equivalent, interpretation wise they are a bit different. So I put in the Gaussian process with a covariance kernel or a covariance function that has to be a positive definite function. So you have to go into Bochner's theorem and look at, or a characteristic function of a random variable, but keep in mind you also want it to be monotone, because typically a covariance function tends to, or you want it to be something statistically interpretable, so you would like the covariance to drop as the distance becomes larger and larger. And if you actually bring this in here, then your biomass basically becomes, this distribution over a finite collection is a normal distribution with the regression component and a covariance matrix, spatial covariance matrix, and typically it has these 3 parameters. All 3 of these are related to the 3 vertical, the 2 horizontal and 1 vertical bar that I showed in that graph previously. Okay, this is the spatial variance. So that is the difference between the 2 horizontal bars. This is the decay, rate of decay, for example. So beyond what distance will the spatial correlation die? And then this is the measurement error variance. All right, so that's the nugget. So that's the lowest value of the variogram. And then in prediction, I particularly have been, a big proponent of the Bayesian hierarchical modeling paradigm, particularly because it makes the inferential paradigm quite simple. Probability of unknowns given known. That's all I need to know, and hopefully with whatever my tools that I have at my disposal in terms of probability models, I can actually build probability models to go to probability of unknown given known. So that's basically how Bayes' theorem helps us get there. Prediction in particular, now any arbitrary point can come in, and so now you look at probability of y of L naught given the data. So that means that all other parameters, so that includes this theta, these 3 parameters in the covariance kernel, and the regression coefficients in beta, they have been averaged out, okay, as a posterior. And the key point about this function, why I said that this has to be a very special function, you cannot just go to bed, dream about a function and put it in, is that, well, this distribution needs to be valid. And therefore, this particular conditional variance has to be valid. So that essentially means that this k theta has to be a positive definite function, not just for one particular set of locations, but for any arbitrary finite collection. Whatever way you construct that k theta, for all values of sigma and phi over their support, it has to be positive definite. So that means the kernel has to be a positive definite function. And here is the magic. So this is something that I really, it took me a while to appreciate this during my student years, but then I realized. I'll show you this thought experiment, and if you're a student here, you can try this simulation and you will see what is so interesting about this. The left-hand side, this picture I already showed you, it is the data, all right? Now, what I do is, I don't look at that high resolution data, I take a very sparse sample from there. Not a very sparse sample, but out of the 115,000 plots there, I took a sample of about 530 plots across the US. Random sampling is what we do, I did that. Okay, if I actually fit a linear regression model and then I actually tried to predict with that sample data, you see this is what I will get. Ordinary linear regression. Why? Because you can still do that. You have x's at all the other points, your NDVI is available, but you can try to predict. But you see what happens because of the random sampling, the sparsity that has been introduced, you are not even able to come close to the actual truth. But if I show you the second model, with the Gaussian process, with the spatial process in it, and do exactly the same exercise, I'm able to get something like this, which looks much more like this than this does. So this is the magic of the spatial process. The only thing that actually is driving this predictive performance is the property of the Gaussian process that it actually is an excellent interpolator, and it actually borrows this strength or incorporates this idea that if you are close to me, you're going to be close to, you're going to be close in value to me. If you're close to me geographically, you are going to be like me. So that's the kernel, and that actually helps us do that. So this is my very quick short course in spatial statistics. Basically, this is why spatial statisticians over the years have actually tried to embrace the Gaussian process and have tried to understand its different properties, particularly with respect to spatial interpolation and prediction. Okay, I'm going to move now. So this is all Euclidean domain. Essentially, there is obviously some distortion of a map projection from the sphere. That's actually very interesting. And there are some geodesic computations that you can do to try to get covariance functions to work on the sphere. Ellipsoids as well becomes a little harder. But in the end, if you're looking, for example, in a closed region, like even the map of India, and you have a good map projection, then you will be pretty much okay in terms of the statistics. The one thing you should not do, for those of you who are interested in spatial statistics, is don't just take the latitude, longitude, that is the spherical coordinates, and apply Euclidean distances on it. Either project it to an Euclidean plane, use that, or you can actually try to get a covariance kernel for the sphere or for the ellipsoid. Both are available, but don't do something as simple, because the scale will completely get lost. The covariance function is valid based upon the underlying topology. So that means obviously you want to have, if it's an Euclidean metric or Euclidean space, then you will want to actually have a covariance function that will work there. Otherwise, you'll have to go to other types of objects. Okay, but now let me move to wearable devices and mobile health data, because this is an important area that is coming in, and it has its own things. Oops, sorry, I think I jumped a slide. There you go. Okay, so you can wear a watch, smart watch as they call it nowadays, and that watch monitors, for example, your movement, your blood pressure, your number of steps, your oxygen levels, and maybe a lot of other health attributes depending upon what your doctor has asked you to monitor. And you can get them fitted, you can get them customized, and so on. And this technology is only growing and becoming more pervasive, and also becoming more and more affordable across the world. So what happens here is that you basically are wearing that watch, and it is actually connected to a server that typically is owned by the company that has manufactured the watch, but you can actually get that data if you actually approach them and so on. It's put in a cloud server. The interesting thing is that the locations now, okay, you have a cloud, because let's take a look at this left-hand side. What you have is this individual who's moving around, all right? And this individual is moving around maybe over many days, or this could be a group of individuals that you're studying over a single day, whatever it is, cross-sectional or longitudinal. But you have a data set like this. This is what we call a trajectory cloud. Not much pattern there. Even if you do some kind of descriptive statistics to try to bin and get out some filtering, you can get the data from there. This is called log of magnitude of acceleration. I'll explain that in a second. And there's a scale there. Let's not worry about that also right now. You can get some values that are high or low. And this is a part of my university campus where I work. And this is over a number of people who have been walking around and so on whole day. So how much activity are they doing while they're at work? That is being being monitored. The question is, how am I going to actually analyze this type of data? Because these are not really very Euclidean. Okay, but the important thing to note before I get to the spatial part is this role of these wearable devices has been quite impactful, particularly in the domain of biomedical health and public health. So what it does is typically, for example, here's one example of what is called spatial energetics. Okay, they actually collect the data. What they calculate is called the MAG, which is nothing but the magnitude of acceleration. What engineers and biomedical scientists have discovered is that if you actually want to look at your metabolism over a day or over a month or over a period of time, looking at the velocity with which you walk, for example, is less important essentially than the magnitude of acceleration. So how many times are you accelerating? That actually helps stabilize your metabolism much better. So the MET is the metabolism, MAG is the magnitude of acceleration. So what that device does is it actually calculates your acceleration throughout your day. How many times are you accelerating and what is the magnitude of that? And if you're going on a constant velocity, it's 0. Okay, and obviously if you're sitting, there is no acceleration, so that's okay. But it will just record everything, your entire movement, and you can actually calculate the magnitude of acceleration. And the way it does it is nothing more than high school physics, just discretized. So acceleration is a derivative of the velocity, so it will just take little epochs and discretize the velocity and get an average over those epochs. Let's not worry about the numbers because there are different scales people use, different companies actually report in different scales. But the point is that if you have a scale on the magnitude of acceleration, you can map it to a metabolic equivalence of task, MET, that is what it is called. And it is a measure of how active you are, all right? And so if you are in the range of between 0 to 3, then you are in sedentary or light and your doctor may say, no, you need more exercise. If you are in moderate level, then that is the level that I am in actually. That's 3 to 6, which basically means, you do a little bit of running, walking, swimming, whatever, but you're not really very active. If you are in 6 to 9, then you are a hard, active, pretty active person. That basically means you spend a lot of hours in the gym. Maybe you play in an amateur football club, but you're not a professional. And very hard is where the professionals live. So that means they do that for a living. Okay, so they have their own trainers and they have a very strict regimen and they're going to basically go ahead and do that. So this maps to this basically through linear regression, nothing more than that. And there are some nice ways to do that. This technology has done one major thing. Previously, if you really wanted to get a good metabolic equivalence of task estimate, you had to go to your clinic. They would put on an oxygen mask on you. They would make you run on a treadmill. And they would actually do a series of experiments and get measurements. Now you don't have to do any such thing. You just do your regular thing, like walk around the ISI campus every day. It will automatically go to the server. It will then get downloaded by your doctor's office, and the doctor's office is then going to be able to say how your physical activity is going on. And it's not easy to cheat your doctor. That means, let's say you actually are not doing as much activity that your doctor prescribed, but you go and tell the doctor, oh, no, I'm actually doing fine. Well, the doctor can now see the data and say that, are you really doing your exercise or not? So one important part here is, okay, you still have points. Locations are still there because you are measuring the data on these locations. But the interesting thing is that if you really want to be a statistician and model dependence now, okay, it's not like your covariance kernel with Euclidean distances between S and S plus H anymore. That's not going to work. Because, you see, for example, if I did not show you the trajectory, this would look just like points on Euclidean plane. You could calculate like, an exponential function is in fact a positive definite function and is monotone decreasing. Beautiful candidate for a correlation function. So you could actually do that. But then, basically it's only going to look at proximity and it will say that. But here it's not proximity. Because you could go, let's say, round and round. You can come back to the same point, or the points may be very close to each other, but you're moving around a lake. Your beautiful, the lake we have right there, and you may be coming back close to that point. So it's actually on the trajectory where you are. Okay. So basically here, for example, you have a detour here in this scale. You see this is a small detour, but you can still see that. So even though the distance between these 2 points is very close, there's a little detour. It could even be more. Okay. So that's something we have to keep in mind. So that means the Euclidean covariance kernels don't work. Secondly, this trajectory and the path that this individual is going to take, you have absolutely no control over that. So essentially you cannot suddenly say, okay, let me try to use some of the math I have learned in ISI and I'm going to try to model this as a manifold. This may not happen because it could just become like a circle, closed curve or something like that. And a lot of the theory will break down and it will also not be statistically appropriate to do it. Because in the end, if you notice what is going on is that the location here is a function of time. That's the one key observation and then the model becomes different because because I'm moving around, and where I am is a function of what time I am in the day. And I have to accommodate that. Because otherwise, think about this. If you're going in a circle and you come back to the same point, okay, you have two data points at the same location, that actually as a realization of a spatial process is going to become degenerate. And so you will not be able to do any kind of inference. So this is where the technicalities come in, and we have to be a little careful. So let's try to see how I'm going to actually do this. I will need to formalize this in a way so that I can build a Gaussian process model, because Gaussian process models are particularly versatile in terms of prediction. They may not be the only ones, but at least in this talk I will focus on that. But I want to do that over this particular trajectory based data. So the gadget that actually fits inside your wearable device is called an actigraph. Okay, that's the one that actually measures where you are, or records where you are, and also transports the information. So you have gamma, and then you have a collection of gamma t, and t is time, and t has its own domain. You can make it from 0 to 24. If it's 0 to 24 hours, doesn't matter. If you're sleeping, that's fine. You can just collect it. This is your domain. Okay. And then the gamma t basically is a curve, basically the position vector at time t. So at time t, it gives you the coordinates or the location where you are. All right, now I need one other index because I'm going to have many subjects, okay, and I'm going to be looking at data there. So you have I equal to 1, 2, so on, who are going to be indexing the recordings, and they're going to be subject day pairs. So it's over many days and over many subjects. You can actually arrange it that way. So in the end, you have a random variable y sub I, where for the ith subject, and that particular measurement has come from at time point t and location gamma t. It is vitally important to have both these arguments inside the stochastic process, because as I said, you could have two different time points, but you could have the same location. So you have to basically make sure that the t and the gamma t are separated. And so over this whole gamma and over this t, you basically get this whole collection of random variables, okay? And in concept, the I is obviously a finite set because its index is a subject, but in terms of this, these are uncountable. This is an uncountable set in concept, because you might be interested in predicting at a completely arbitrary time point and location. All right. Now here comes the one slide on statistical modeling. It's a little bit dense because these data are, after all, a little complicated, but we have the ingredients. So let's say y sub I gamma tt is basically the response. You have mu I gamma t t beta is the mean structure. You have wi gamma tt is the spatial random process. You have the measurement error white noise variable, as we call it. And as I said before, even if this is not a valid stochastic process, no harm in this level, because you're going to look at the finite data part, and they're all going to be IID with perhaps different variance components for each subject. So you have a fair bit of structure here, and this particular mean function could, for example, include covariates and regression coefficients that could also depend on the time. The question is, how am I going to construct a stochastic process, a Gaussian process, on this type of trajectory with almost no assumptions on the geometry of the path or the curve? All right. So there are some simple ways, which are not terrible actually, but nevertheless, they will give you valid models. So one such thing is to look at Wi, this particular process, separate it or split it up into a purely temporal process plus a purely spatial process. Now that can be done. You have to be a little careful in how you construct the spatial process because it is now purely gamma t, but you could run into that same problem of degeneracy when it comes in. But if you have fairly balanced data, filtered data, then this model has been used in actigraph data analysis, particularly by the engineering community. For us statisticians, we want it to be a little more flexible, and we also like to look at covariance kernels and functions that way. So let's suppose I look at each subject, and each subject over I will independently follow a Gaussian process with a covariance kernel. What I can do is get into my space-time covariance kernel and modify it so that it becomes suitable for an arbitrary trajectory, keeping in mind that it has to be a positive definite function. And one simple way to do that is to take in these two arguments, let's say gamma t, take this as one particular object, as the first object into your covariance function, and the same object at t prime. And then take a space-time covariance function that you know is valid, replace the location with gamma t, and keep the time as t minus t prime. You're done. It's a valid stochastic process, it's a positive definite function, valid kernel, predictive inference is valid. You will not get degeneracy even if that individual is coming back, because even when, for example, you have two different time points, but you have the gamma t and the gamma t prime become identical, well, okay, fine, this becomes 0, so therefore this guy becomes 1. This itself is actually a valid positive definite kernel. So you can still work that out. Statistically, interpretation-wise also it's attractive, because after all, if the location themselves are actually closed geometrically, then you don't expect that kind of correlation there. It's driven by time, that correlation, and that's captured. Okay, and then you actually look at the collection of the realization and you build a multivariate normal distribution and everything falls in place. And if you are a Bayesian, you don't have to be until this point, but if you want to do full learning of the entire stochastic process and you want to do that through a Bayesian hierarchical model, then, well, all you do is come right up here. This is basically your likelihood conditional on the spatial random effects, regression coefficients, the measurement error or the white noise variance. Then here's the spatial process. We now know how to construct it, and then you have the priors. If you don't want to be Bayes, you can delete this part. You can look at this. This is the known given the unknown, but then you will have to be a little careful about the type of inference that you are going to do, particularly with regard to the asymptotics. Predictive inference will follow in the Bayesian hierarchical paradigm by simply sampling from the posterior, and then at the new time point, whatever time point your client gives, you will jointly model this, the predictive value and the predictive random effect given the data, and you don't do integration, you do Monte Carlo sampling. So that's the computational part. So you can look at it this way. First you sample from here, then for each drawn sample from Wi, gamma, tau and theta, you draw a random effect at t naught, then for that value you draw a value from the likelihood, and that's your predictive inference. So that is exactly how it goes. You have marginalized, you basically have done, let me go back, you have basically, sorry, I think I'm stuck here, right here. You've basically done exactly here, everything that I did here, but on arbitrary trajectories with no, almost no new, or rather, sort of very complicated mathematical assumptions on the geometry of the trajectory, because you just don't know how that individual is going to move around. Okay, this is not the only way to do this. I do want to say that you could actually build geodesics into your model, and that's actually not too bad, because for example, you can look at a spatial process as a kernel convolution of, let's say, a white noise process. So if you, for example, are looking at trajectories, and you can actually look at this kernel, e to the power minus, and this d is the geodesic metric between the points. Now you see the problem, the general problem is that if you take a geodesic metric on, let's say, some kind of arbitrary curve and put it into a covariance function that is well defined on Euclidean plane, that may be lost, because that covariance function may not be, valid covariance function on other spaces. But if I take this approach, this is like, when the problem becomes mathematically very difficult, try to change the problem. Well, then, you can actually get this geodesic distance, you can plug it in here. Whatever this value is, because it's an integrating or a kernel convolution of a white noise process, this will be a valid stochastic process. I don't have to worry about that. So that way, if there is interest in geodesic distance modeling on trajectories, you can build that. If, on the other hand, you can discretize and you want to build dependence through a graph, that's also possible. So now you get into the graph Laplacian. But what you do essentially is you take a proximity matrix W, you construct that on your entire data through any kernel, whatever kernel you like. And then you actually build the graph Laplacian through this construction of this A, and D becomes the diagonal of the W, and then you construct this A, which is D to the power, the reciprocal square root of the diagonal elements multiplied by W, multiplied by that itself again, and you get the graph Laplacian, and it's fairly easy to actually constrain the value of the rho to make sure that this matrix is positive definite. So this is more of a finite dimensional inference tool that you can use for this type of data, where you don't have to worry about positive definite kernels. All right, but how about model performance? So I have all these different approaches, which one works well and which one doesn't, okay? So let's take a quick look. This is the most general one, okay, the model one, the one that I told you about, taking the space-time covariance kernel and just switching it or adapting it to trajectory data. This is the more like the engineer's favorite tool of additive processes, purely temporal plus purely spatial. Then here is a kernel convolution with geodesic distances, and model 4 is the spectral graph specification with geodesic proximities. Each of these metrics, I won't get into the details, but they are basically model comparison metrics, okay? So for example, in machine learning, you will see the WAIC, widely applicable information criteria, or the root mean square prediction error being used a lot. The posterior predictive loss is a Bayesian decision theoretic approach to predictive loss. The second G here is a ISI alumni Shujit Ghosh. And then DIC is another Bayesian predictive loss based model comparison metric. If I take model 2, which is this engineer's benchmark, so to speak, as the benchmark model, then I see that 1, 3, and 4, all three of these models beat model 2. They outperform model 2, and they do so by varying degrees. So for example, but if you look at the gain in terms of the posterior predictive loss of information, okay, what is the minimum? So that's the other way around. That means the higher the value here is better for the model. Then you basically see that the posterior predictive loss here compared to model 2 is the lowest. So this model 1 does the best, and then model 4 does the second, and then model 3 does the worst. But model 2 is actually the worst. All three of them actually outperform model 2. Okay, all right. Last segment of my talk, now comes the question about AI and artificial intelligence. So this is, until now, life was pretty good for statisticians. We were able to actually build models. We were able to actually get an inferential framework to handle actigraph or mobile data, especially if you're interested in spatial dependence. All right, now let me show you this little transaction. This is actually a real simulation, and it is actually between me and a computer in UCLA. Now, this is not live. I thought of doing it live. I can do it live, but sometimes, with the internet and so on, I don't know if it will work. But it's almost real time. So I, being the patient, I ask this AI engine. Nowadays, it's all conversational through a large language model. Hello, I want you to analyze my metabolic activity levels over the last month. And I give it my ID. Okay, here's my UCLA ID. So because my doctor is part of my university, he actually has access to all that, but I'm not talking to the doctor right now. I'm talking to a machine. And the machine says, sure, I can help with that. Give me a moment as I look up your profile and collect the data from your accelerometer, which is like an actigraph. That's basically your wearable device that you're wearing. A few minutes later, and this is not few meaning like literally a minute or two, not more than that, it will say that I have completed my analysis. Your current metabolic activity level is light. And I'm like, okay, that's not good. So I have to do something about it. So I say, well, can you recommend a new path to me for doing my daily walks so that I can upgrade my metabolic activity level to moderate? And at that point it says, okay, this is the key part. This is why a lot of the methodological issues that I talked about becomes important in this interface. Let me predict, and predict is a key word here, your metabolism rates on 13 new trajectories that are close to your daily walking routes. Now, it knows my daily walking habits because it has my ID and it's all my data. What it is going to do is it is going to train. It is going to train on my walking habit and it is going to estimate, which it did here, my metabolic activity. But it also knows where I walk. So what it's going to try to do is during my daily walks, it's going to not go somewhere far away. For example, if you're walking here in the ISI campus, it's not going to send you to Victoria Memorial. It's going to say, well, let me see if I can look at the attributes, the geographic attributes of your walking surroundings and try to see if I can recommend something better for you. And it says that I am able, and this takes about 5 minutes on the current platform. It's a lot of data, mind you. I'm able to recommend to you a new trajectory from your home to your office that should yield a statistically significant increase in your metabolic levels. So in other words, it has actually looked at arbitrary sets of points where it knows that there is a walking path, and it has actually used the trained data, my data, to train itself and now predict what my metabolic levels are going to be if I follow a string of gamma T's that is provided to you. So that's why I kept saying, as long as I'm able to predict at arbitrary trajectory points, I will be able to do that. So the model will not collapse, the model will not break down with a Cholesky decomposition problem because it's all positive definite and valid stochastic processes. So this is what I just gave you an example of is essentially a large language model, and computer scientists have been doing natural language processing for a very long time. Even in this institute, there has been an enormous amount of work in that domain. So many of you probably know this much better than I do. But one thing I do want to point out is if you look at this size, particularly the number of parameters of the corpus size for these different private sector funded large language models, there's Amazon, there's ChatGPT, there's Google. You're going to see that particularly almost 2019 onward, there has been a massive explosion in this corpus size, or which is basically the number of parameters, essentially, you can say, in your deep learning network. Okay, so you have a deep convolutional neural network that is going on. It could also be a recursive neural network. It could be a variational autoencoder, but a deep one with many, many, many parameters, and you want to basically try to use it. Okay, now I'm a statistician, and the thing is I don't want to get into natural language processing. I don't want to get, in fact, into that particular algorithm and what it does, because it's, first of all, I'm not qualified to do so, and it's good to be humble when you don't know something, and it's also just going to be almost an impossible task given the amount of complexity that has gotten into building those engines. But my question is, just go back to that previous interaction with that machine. If I am able to tell it or train it to do statistics, how can I do it? Okay. So the way I look at it, and this took me a little bit of time because I was trying to understand, and I'm not as smart as many of you are here, so it took me my own sweet time. But I think I finally got a grasp through a lot of, going back to my graduate school hat, doing some programming and so on, and finally figured out a few things. But here's the basic idea that I want to use. I am given a function, a very arbitrarily complex function with a data and a model and some neural parameters that I'm basically calling phi. Those are parameters inside the neural network. And if I put in an input, that is a y and a model, I will get an output. So this is an engine where you can put in any input you want and it will give you a corresponding output. It's an input-output mechanism, okay? What it does very well is if you are actually able to give it a very large number of inputs and a very large number of outputs, then that's called supervised learning, and you can actually train it so that with an optimal phi star. And that basically minimizes an expected loss function, and it gets you this optimal value of the phi star. And so basically what goes on is you generate from the model data and theta, no real data at this point, complete simulation, data and theta from the model, and then you actually do an empirical optimization of any loss function that you want, that you specify, and you get the optimal neural parameter. And this training step takes a very long time. So people who complain about MCMC, for example, and that may take hours and so on, this actually also takes hours and hours to train. But here's the big advantage. Once it is trained, no matter how many data sets come in, okay, from that same domain, the data gets inputted, it in a fraction of a second is going to give you the output in terms of, you know, this inference that you want. So for example, this could be a vector of median and few quantiles or whatever you want to look at, posterior mean, posterior median, posterior quantiles, whatever. And so the data then gets fed into it and you get the output. So to try to wrap our heads around this, because this is a new technology, and I think I'm not the only one when I say that some statisticians are still grappling with what is our role in this world, you know, how to use it. And I would say that, well, think about it this way, that this is an engine, a tool that can actually amortize. This is the word that I used here, amortize. Amortize is used in this particular domain. Basically, it says what? Amortize for the, in the business world is basically that, you know, value that essentially has some value and then it gets amortized or decreased or adjusted over time. So here the value is the cost. And the idea is that when I am training, it's a very expensive proposition, but once I have trained it, I am in amortization. So that essentially means that immediately new data comes in a fraction of a second, I will be able to deliver. So all we need to understand is feed in a model, generate data. As a Bayesian, I will also generate the parameters, but if you are a frequentist, you don't have to. You can have an Oracle model, and then you can actually go ahead and train it like that. So that's amortized Bayesian inference. And let's see, I think I am stuck here a little bit, maybe. Okay. All right, here it is. So one important point, there's another machine learning technique that actually comes in becomes very helpful because you have to train it, and training takes a lot of time, and it has to be done through a large number of simulated data sets. Doing any type of inference that we are used to, whether it is the EM algorithm or MCMC, it becomes very, very complicated and very, very time consuming because it's an iterative algorithm. Every time it has to iterate to convergence. All right. In simple models, yes, you can do it very quickly, but in general, with the complex types of models that I showed, it's impossible. So I have to somehow do some kind of approximate inference and not exact inference. And one thing that in my experience, my recent research has worked well, is to, particularly for Bayesian inference, is to look again at the probability of the posterior distribution, coefficients, spatial process, given y. I'm going to, instead of estimating the kernel parameters, all right, I'm going to fix them over a grid, and I'm going to actually try to find the best convex combination of posteriors conditional on these weakly identified parameters in any case, because they are not, you know, asymptotically consistent. They are basically a bit problematic in any event. So why not fix them over a grid indexed by G and then get an average of that? A very simple example will be that let's suppose you have you know, a normal inverse gamma model, all right? So with in a linear regression, well, that's actually closed form Bayesian linear regression. So I can exactly sample from here, provided I have actually fixed the covariance kernel parameters in my Gaussian process. And if I'm able to do that immediately without iteration, that means this is already exact sampling or even closed form quantiles are available, fine, I'm going to just use that. I'm going to calculate the optimal weights for these AGs and use those optimal weights to actually sample from this mixture distribution. And that can be done very, very quickly. So the only part that is important is how do I optimize the AG? And there is some flexibility there because you can do it in a completely decision theoretic way, or you can do it in using information theory, or you can do it using you know, cross-validation and so on. So as an example, if you use posterior predictive loss functions in a decision theoretic way, it basically becomes the values of A that minimize this essentially squared error loss function with the posterior predictive distribution. And you can calculate this average over a validation set. And the posterior means are, on the other hand, calculated on the training set so that you don't necessarily need to penalize this. If you don't have validation sets and training sets, you want to use the same data twice, fine. You can take that, but then you adjust for a penalty. And you can do that. And that may, like AIC, WAIC, and a lot of other metrics actually help to do that. Another example is to take this log scoring function, and that actually gets us asymptotically equivalent to a minimization of a Kullback-Leibler divergence between the true posterior predictive and a mixture using this leave one out cross validation. There's a very nice paper by Bertrand Clark in Bayesian analysis, in the journal Bayesian analysis, where he actually lays out this whole framework. And so we're basically using that. And so you can actually get the AGs from there. It's a convex problem because it sums to 1, and you want the A's to be non-negative so that you have the, you are able to get them as probabilities that you are going to be sampling from. And then finally, big data. There's a lot of data. You can actually do the stacking. So first you divide the data in streaming data, particularly like active graph data. It comes in any case over time like this. So what you can do is you can go through the first time point, do the stacking to get your quick, fast inference, approximate inference that's admitted, but nevertheless very quick result on the posterior predictive and the posterior distributions. Get that, and then go stream by stream as the data comes in, and then again average over these different data to get a weighted average over that. So data partition, local inference, and then global inference. And that's the structure. Nothing more except to be careful about making sure that however or whatever loss function you take, you still have a convex optimization problem that will converge, and you will be able to get that. But there's enough flexibility here to explore and figure out what exact decision theoretic paradigm you wish to pursue to get this approximate. Okay, quickly to the spatial energetics case study. Obviously, you can put in covariates, predictors that you want to control for or you want to learn. So here, for example, I'm not going to get into too much detail, but we took the baseline as an Asian female with age less than 25 years, and then we basically looked at different races, and then we looked at different age groups. And what you see essentially is that compared to the Asian female with age less than 25 years, for example, these other age groups are showing lower average metabolic equivalence of tasks. So this is a very, very active group that you can see. The males do a little bit, typically depict a bit higher metabolic equivalence of task, but then there are also different races that also tend to do a little higher than the Asian females, for example. This is a particularly useful one for every single subject over the entire period of time. Every day, you can actually map or this trajectory over time of the metabolic equivalence of task or the magnitude of acceleration. So you can see the bumps where that individual is getting more and more static and so on. So typically, it goes after adjusting for the other confounders, risk factors, covariates, and are plotted at the residual scale, so that if there is an underlying pattern here or underlying factors that may be affecting this particular individual's daily periodic behavior, then you will be able to statistically estimate that. And then finally, here's a prediction problem. And the prediction problem, as I said, is about what it did, that machine. Essentially, it starts and ends. So, it actually, the data is never really very continuous because there's missing data, there's technological gaps, it's pretty noisy and so on. But the framework I showed you is something that actually can work in a very robust way without you trying to go, without human, let's say, intervention in data analysis, which is what these AI engines typically want, because you just feed in, train, and as long as you're able to do that, it will be able to learn. But you have to do that over a very long period of time. And then again, you can see how it smooths in and predicts the interpolated values in between how I'm going to do in terms of my magnitude of acceleration. Finally, you can also look at the physical activity profiles for these individuals. Again, these are centered around 0, but you can see where the high bumps are, where the low bumps are for each day. And very interestingly, if you are actually consulting for a sports team, maybe like Kolkata Knight Riders, you can actually provide this, at least in the US, the sports teams are very interested in getting for each player this particular type of physical profile. Their entire periodic behavior, daily data, when it is high, when it is low, and they want to monitor that because it's so critical. Little bit of difference is going to make a big difference. One last point, Gaussian processes are very good interpolators. If you're in an epidemiologic study, then the histograms won't look like Gaussian because of the very noisiness of the data. But if you use the Gaussian process model, you can still actually, because it interpolates, you can still capture the distribution here, which is why Gaussian processes are used very widely in non-parametric inference. Because it's, even though the word Gaussian is there, do not think it is restricted to just data that depicts Gaussianity. All right, and here are a few papers. This is, the first one is actually just accepted in JASA, so you might be able to see that more about predictive stacking and spatial statistics, but particularly if you're interested in spatial energetics, then you can take a look at this paper, which is on arXiv, posted on arXiv. And then if you're interested in Bayesian transfer learning and more AI-based predictive stacking, then you can look at this, which is also on arXiv. So on that note, I'm going to stop. And again, thank you so much for this very gracious felicitation, the invitation, and such an honor to be here. Thank you so much.
So when you use that grid for the estimation, how important is the grid size? Or like
No, that's an excellent question. It does not scale, it scales extremely well with regard to the size of the data, but it does not scale well with a large number of parameters on large grids. So if you have a few parameters, then you can actually still use a fairly fine grid. But these parameters themselves are not very well identified by the data, as you know, right? So therefore, you don't want to actually make that grid unnecessarily fine, because all it is going to do is, let me see if I can go back for a second. Right here, for example, because all it is going to do is increase that value of that capital G there, you see? And that's actually, with regard to the grid size, is just going to give you a large number of models. Stacking usually does decently well with very, very big data sets, because you can use, I didn't go into the details, but Pareto smoothing and so on to actually calculate the leave one out cross validation. But doesn't do that well when you have a very large number of hyperparameters and the grid becomes multi-dimensional. So if it's a low dimensional grid, but the grid has many intervals, let's say 3-dimensional grid, but it has, let's say 10, 15, 20, 30, 40, even 100, it will work fine. But if it is a 50-dimensional grid, meaning R50, it's going to become really problematic. That's where your statistician needs to come out and think a little smartly about how can I solve this problem. And one thing is you can project, pre-process, project the parameters functionally onto a lower dimensional grid, do the required probability transformation in the model, and work that out. And there is something we are doing on that line, but yeah, there are tricks you have to play. Good point.
I also have another question, which is, so when you're gridding these parameters, you're essentially restricting itself into a zone, right?
Correct.
So what happens if it's outside that zone?
Yeah, okay.
Do we have any way of, I mean,
No.
It's obviously gonna be worse.
Yeah, that's a very valid question. I do not know the answer to that, I will be honest, because unless I really have experimented, I will not be able to give you that. But I can give you some intuition, which is actually not very difficult. In particular, for this particular AI engine that I trained, okay, I did it on myself. I was literally the subject. And so I was moving around, I fed it into my data, and I trained it. It knows that that's my domain. Now suddenly if you say that, well, 25 miles out, let's say Professor Srivastava, you still walk around every evening like you used to? So, but now if this machine is saying to Professor Srivastava that go to Victoria Memorial and do your evening walk, Professor Srivastava may not like that very much, and it may not actually fit his, schedule. So prediction wise, if the geographic attributes, I'm not saying it is like that, but if let's say the slope, the uphill, it tends to promote because of acceleration and the effort that you put in to go uphill, right? Exercise after all. then if it's similar, Victoria and ISI campus, then maybe it will do okay. But if it's very dissimilar, it will not. It will collapse. So it's not a cure-all for everything. Absolutely. That's why we are still in business.
Thank you. For those online,
And there is another question, I think.
Now, I was just wondering, so in a spatio-temporal kind of situation, when you have the strong temporal effect, for example, you might have the seasonality. The example that you gave, so I am the same person, I work. But maybe in the summer, 5 o'clock in the morning you will find me. But in the winter, the same person, same locations will come at 9 o'clock.
Correct.
So if that is the situation, how do you handle it?
I see what you're saying. So let me see if look, very good point. Okay. So two things can happen. You can go to, for example, this model, and you can, if you are interested in seasonality in the residual scale, you can incorporate that here. Or you can, if you want to do it in the mean, you can do that through here. Seasonality. So for example, as you're saying, different seasons, you can incorporate that through indicator variables. So it can be adjusted, accounted for. Like all good statisticians, we want to adjust for the extraneous factors, right? So you're absolutely correct. That is something that can be done, but nothing in this framework prevents you or precludes such adjustments. But again, there's a design aspect to this, which is quite broad, quite challenging, in fact, especially if you want to do design studies, and they are being done now. But this talk is not about that. But the point is that nothing in this framework will preclude a design-based study like that also. Very good. Yeah.
So there are 2-3 small questions.
Yes.
One is that you mentioned that during the process of training, you're doing a lot of simulations.
Yes.
Now, if you do simulations, you need a model, right?
Right.
So what kind of, and would that model not impact on your predictive ability after you've trained?
Excellent. Absolutely correct. And the model that I am, so let's go to that right here. That M is the model, as you said. You're spot on. This is specific, the training and this is generative AI. The amortized inference will be specific to the model. Data generated from the model. So one way, Professor Majumdar, to think about this is the following, that typically statisticians, we have been trained like, okay, feed the data, get your estimates, and then predict. Here, when you fit the data, you don't wait for the data. You simulate from a model, train it on a model, predict on the data that you want to analyze. So to answer your question, this is, well, I don't know if I want to use the word replace, but this is substituting in some way the statistical exercise of fitting a model to a data set. But the way I am doing it is that I'm going to generate data from the model, not use the actual data that you're interested in the beginning, train it through that model by generating from that model right there, that generate replicates right here. And then if any other data comes that you would have fitted that model to, not just one data set, but thousands and thousands of data sets maybe, you could use the trained engine almost immediately.
But how would you test the goodness of fit on the actual data?
Yeah, so that is where this loss function comes in. And I'm not saying that this is already, a settled case. There's a lot of papers that are still being written, criticized. But the idea is that, imagine if I gave you, this is nothing more than an interpolation problem of sorts, right? Like if I actually gave you a lot of data and I gave you an interpolator, it will learn from the data and then it interpolates the data and a new thing comes in, it actually predicts. The principle is the same. The loss function here plays a role here. You don't want this theta hat to be very high dimensional. So for example, restrict it to, let's say, mean and a few quantiles. But this loss function will at least try to tell you the discrepancy being matched. Similar to how a neural network is trained, exactly like how a neural network is trained, but using generative data from a statistical model.
So can I ask another question?
Absolutely.
So you talked about these grids, and in these grids, you're essentially restricting yourself to that grid. But I've seen now models where they use another grid which is overlapping with this grid and so on, so they can predict far away.
Far away.
And how do these, I don't work in that particular area, I've just seen those models.
Yeah.
How do those work? Do they work well when you're making these long, spatial projections?
No, absolutely. So I don't know because I should not be answering this because I have not really played with extrapolation through external grids. Climate data particularly, like there's a lot of that. AI is kind of new to me too, and this is just a few things I've been playing with. I'm actually quite happy that I was able to make this work. I didn't think even this would work the way it did. But I don't know, but not everything works well for sure. One thing I can tell you from my experience, even my limited experience, if you don't bring in statistics into this, it doesn't work well at all. Even in my study, if I, for example, just did not specify the model through my, that's why I did the statistics before I came to AI here in this talk. But if I didn't build the GP-based model on trajectories and created that framework for prediction, this would be completely hopeless. Even a very deep neural network will not be able to, it will give you only about, let's say 67% or so instead of the optimal 95% coverage in simulation experiments. So it's quite hopeless. But if you do this, where you're actually informing the model, and then you're analyzing the data, you're actually hitting 94%, 95% in terms of optimal coverages, prediction or estimation even, inference.
One last biological question. You said that it is only acceleration that adds to metabolism.
No, not only, but go ahead. No, I didn't say only.
All right, so even if it's not only, you did say that if you're walking at a constant speed, it won't impact on your metabolism, but that's not true.
No, that's not true.
You're losing calories,
It will impact. It will impact. I didn't mean to say that it will not impact, but what I said was that the literature, particularly in the spatial energetics domain, is focusing on predictive value of MET, metabolic equivalence task, on MAGS, magnitude of acceleration. And let me qualify that statement. If I said that, I apologize for the miscommunication. A large part of this particular domain has come from sports medicine. And they're actually largely looking at sportsmen or high school or university athletes to build them into professional sports. And most of them are very healthy individuals already because they're aspiring to become professionals. So that's why for them, for this particular population, MAG, the acceleration that they put in, these jolts, when they make you run even, I learned this recently, they will make you run in bursts of rapid acceleration to probably promote. But maybe you have other perspectives on this.
I think they look at reflexes. Essentially, they are capitalizing on reflexes, and this acceleration is actually what would I say? Measure of how reflexive you are.
Absolutely.
And these kinds of sports, they
absolutely.
capitalize on reflexes.
And also, absolutely, velocity has an impact. The gradient over the slope that you're walking on, are you just climbing or are you walking flat? That has an impact. So absolutely, there's a lot of impact on that. I certainly do not dismiss that.
Thank you. For the viewers online, if you have any questions, please feel free to ask.
Oh, there's a question. Okay, there's 2 questions actually here.
So sometimes you may have a spatial covariate also.
Yeah. Absolutely.
So how hard would that be to incorporate it here in this model?
Okay, that's also a very good question. If you do have a spatial covariate that you believe is adequately captured by a linear regression, then what I have there in that second bullet should pretty much do it. But you might have seen recent work, including by one of ISI's alumni, Abhirup Dotto, and 2 of them actually, and Orko Jyoti Shaha. They actually wrote a paper in JASA on spatial generalized least squares. We're actually using, spatial random forests. And they basically actually talked about nonlinear modeling. They modeled this part with a random forest, and they modeled this part with a spatial latent process like I am doing. And the argument is that this part is very, very complex with maybe other types of spatial information or other types of covariates even. And so it's not an easy direct question to answer, but if you think that spatial covariates, like these are all indexed by gamma t and t, so you can put in, for example, the slope at that location. That you can put in here, no problem, because you adjust for that and then see what else is available or captured by the process. But that will help improve your prediction. So if you have spatial covariates, you should, in my opinion, for a prediction problem. Nowadays, overfitting is not as bad a thing that it used to be, particularly with these machine learning tools. So you might as well use it.
Are there any more?
I just have two simple questions what type of mobile health data are more suitable for this type of model, and what are the main challenges in this model, like any noisy or any biased location if present in the data set already?
Okay, yeah, very, very good, very, very good questions, absolutely. So what type of mobile health data are possible? This is actually a very loaded question because I think it's not just also the data, but the question that you're wanting to answer, right? So for example, mobile health data are being used a lot as biomarkers, but not as a response. So for example, in my talk, if you notice the main outcome here is actually coming from the Actigraph, which is this mobile health device. And therefore the outcome or the response itself has to be modeled over the trajectories. But if, for example, you're going to use your, let's say, some kind of metric from a mobile health device, like maybe your blood pressure, how much it fluctuates over the day, and you want to use that, let's say, as a predictor, as a risk factor, as a biomarker for a other type of study where the data itself is on the subject's health, then you don't need this model or this complexity at all, because that will become just like a predictor, and you can still use machine learning to try to interpolate or smooth or so on, or debias it, as you said, because you are right that this sort of data can often be very, very noisy. So I did not refer to that paper, but in 2023, I think I published a paper with a few collaborators in the Annals of Applied Statistics, where it was mostly about bringing this type of data to statistical modeling. So there you will see how much of pre-processing of the data had to be done to get there. But if you want to use it as a biomarker, you don't necessarily need to go into that much of detail. The GPS coordinates itself, that's actually a pretty complicated thing, because it sometimes gives you, it loses the signal sometimes, and you don't know where you are suddenly for a little bit of time. So you have to, that's why there are those gaps, and you have to predict and interpolate. All very good questions, very relevant questions, absolutely.
Thank you, Sudipta, for the talk. And we can break for now. And we have tea and snacks outside. And we can come back in 15 minutes for the cultural part of the program. Thank you again, Sudipta.
Thank you.
See.
Hello, check. Hello, check. Check. Hello, check. Noise can ask. Check. Hello, check.
আমি আমার মাইক ঠিক যাবে একটা বলে ও হারমোনিয়াম বাজাবে ওর হারমোনিয়ামটা একটু লুজ
টেবিলটা একটু অ্যারেঞ্জ করে দেবেন এই এটাকে সরাতে হবে এটাকে সরাতে হবে এটা বন্ধ করুন এটা বন্ধ করুন এটা কেন এখানে এটাকে ডিসপ্লে করেছে কেন হ্যাঁ এটা এটা বন্ধ করুন দাদা দাদা কিছু দিতে হবে না পুরো এটা তুলে দিন
এইটা করতে তো
এটা এলো কোথা থেকে এটা বন্ধ করে দাও পুরোটাই বন্ধ করে
কিন্তু ওটা ফ্লাইট মোড করে দেবে গান যদি ফোন চলে আসে বা এই চলে
বন্ধ
আসে
করো
ঠিক আছে
একটা টেবিল আছে ওই টেবিলটাকে একটু গানের সময় রেডি করে দিতে হবে ঠিক আছে দুজন গান গাইবে যখন
অনলাইনে চলবে না ডাউনলোডেড গান আছে হ্যাঁ তাহলে ঠিক আছে হ্যাঁ ফ্লাইট মোডে বেস্ট ফুলটা ফোন চলে এলে
यादें में प्रस्फुट
Hello, hello. Good evening, everyone. It is truly special to see so many familiar faces come together today. Faces that carry not just memories of classrooms and corridors, but stories of friendship, dreams, and journeys that began right here. Today's evening is not about performances alone. It is about remembering, revisiting, and reconnecting through music, movement, and words.
Indian art has always believed that movement is prayer and rhythm is reflection. The opening presentation is a dance inspired by Rigvedic sloka, a humble invocation seeking mercy from the ultimate supreme, reminding us of our tendency to mistake ourselves as equal to the divine and gently guiding us back to humility. অহংকার নয়, শ্রদ্ধাশীল মনই হলো সত্য ও সুন্দরের পূজারী. With that, let's invite Shreya Chatterjee to the stage.
यादें में प्रस्फुरन्निव धृतिर्नादमातो आद्रिवः म्रीरा सुक्षात्रा मृराया यादें में प्रस्फुरन्निव धृतिर्नादमातो आद्रिवः कृत्वा समहदीनता प्रतिपं जगमाशुचे व्रीरा सुक्षात्र मृराया यादें में प्रस्फुरन्निव धृतिर्नादमातो आद्रिवः अपाङ्मध्ये तस्तिवांसं तृष्णा विदर्जरितारम् अपाङ्मध्ये तस्तिवांसं तृष्णा विदर्जरितारम् मृरा सुक्षत्र मृराया मृरा सुक्षत्र
यादें में प्रस्फुरन्निव धृतिर्नादमातु आद्रिवः
Thank you for such a mesmerizing performance. There are moments when the heart feels deeply but cannot explain why. The next song speaks for that quick confusion, the vulnerability of love, the softness of unanswered emotions, and the beauty of feeling without logic. This song flows gently yet leaves a powerful echo behind. May I now request Shevanti Basu to come on the stage.
Hello. Hello. ऐसे क्यों कुछ तो लिखती हूँ, लिख के मिटाती हूँ मैं रात भर। ऐसे क्यों बातें खुद की ही खुद से छुपाती हूँ आजकल। ये सारे सच गलती सब कुछ पास फिर से रोने ऐसे क्यों ऐसे क्यों उसके होठों पे अच्छा लगता है ऐसे क्यों कुछ भी बोलने में मन में होता है इज़ाफ़ा gives us courage. The courage to speak truth, simply and honestly. The next performance is a reflection on sincerity, ethics, and quiet strength. কারণ সত্যের পথে চলাটাই জীবনের মূল মন্ত্র হওয়া উচিত। With that, let's invite Srijan Chattopadhyay to the stage.
হ্যালো হ্যালো। বোঝাপড়া, রবীন্দ্রনাথ ঠাকুর। মনেরে আজ কহ যে, ভালো মন্দ যাহাই আসুক, সত্যের লও সহজে। কেউ বা তোমায় ভালোবাসে, কেউ বা বাঁচতে পারে না যে। কেউ বিকিয়ে আছে, কেউ বা সিকি পয়সা ধারে না যে। কতকটা যে স্বভাব তাদের, কতকটা বা তোমারও ভাই। কতকটা এ ভবের গতিক, সবার তরে নহে সবাই। তোমায় কতক ফাঁকি দেবে, তুমিও কতক দেবে ফাঁকি। তোমার ভোগে কতক পড়বে, পরের ভোগে থাকবে বাকি। মানধাতারি আমল থেকে চলে আসছে এমনই রকম। তোমারই কি এমন ভাগ্য, বাঁচিয়ে যাবে সকল জখম। মনেরে আজ কহ যে, ভালো মন্দ যাহাই আসুক, সত্যের লও সহজে। অনেক ঝঞ্ঝা কাটিয়ে বুঝি এলে সুখের বন্দরেতে। জলের তলে পাহাড় ছিল, লাগলো বুকের অন্দরেতে। মুহূর্তেকে পাঁজর গুলো উঠল কেঁপে আর্ত রবে। তাই নিয়ে কি সবার সঙ্গে ঝগড়া করে মরতে হবে? ভেসে থাকতে পারো যদি, সেইটে সবার চেষ্টা। না পারো তো বিনা বাক্যে চুপ করিয়া ডুবে যেও। এটা কিছু অপূর্ব নয়, ঘটনা সামান্য খুবই। শঙ্কা যেথায় করে না কেউ, সেইখানে হয় জাহাজ ডুবি। মনেরে তাই কহ যে, ভালো মন্দ যাহাই আসুক, সত্যের লও সহজে। তোমার মাপে হয়নি সবাই, তুমিও হওনি সবার মাপে। তুমি মরো কারোর ঠেলায়, কেউ বা মরে তোমার চাপে। তবু ভেবে দেখতে গেলে এমনি কিসের টানাটানি। তেমন করে হাত বাড়ালে সুখ পাওয়া যায় অনেকখানি। আকাশ তবু শুনিয়ে থাকে মধুর ঠেকে ভোরের আলো। মরণ এলে হঠাৎ দেখি, মরার চেয়ে বাঁচাই ভালো। যাহার লাগে চক্ষু বুজে বহিয়ে দিলাম অশ্রু সাগর, তাহারে বাদ দিয়েও দেখি বিশ্বভুবন মস্ত দাগর। মনেরে তাই কহ যে, ভালো মন্দ যাহাই আসুক, সত্যের লও সহজে। নিজের ছায়া মস্ত করে অস্তাচলে বসে বসে আধার করে তোলো যদি জীবনখানা নিজের দোষে। বিধির সঙ্গে বিবাদ করে নিজের পায়ে কুড়ুল মারো, দোহাই তবে এই কার্যটা যত শীঘ্র পারো সারো। খুব খানিকতে কেঁদে কেটে অশ্রু ঢেলে ঘরা ঘরা মনের সঙ্গে একরকমে করে নে ভাই বোঝাপড়া। তাহার পরে আধার ঘরে প্রদীপ খানি জ্বালিয়ে তোলো, ভুলে যা ভাই কাহার সঙ্গে কতটুকুন তফাৎ হলো। মনেরে তাই কহ যে, ভালো মন্দ যাহাই আসুক, সত্যের লও সহজে। Friendships born in college are unforgettable. Some grow stronger with time while others fade, leaving behind memories that stay forever. This song reflects the quiet strength of acceptance, the beauty of loving without holding on, and a farewell that lingers long after the music ends. Please welcome our next performer, Oisik Bhattacharya, on stage. He will be accompanied by Ahun Chaklo.
হ্যালো হ্যালো এতটা নিচে করো একটু উঠিয়ে দাও সামনে করে দাও মুখের সামনে হ্যালো তানপুরাটা চালা তানপুরাটা হালকা মাইল্ড রেখো আর ওর হারমোনিয়ামটা একটু বেশি রেখো ঠিক আছে tiene tiene
বন্ধ করে দে ফ্যানটা মনে অফ সুইচ অফ কর দুই দিচ্ছি হ্যাঁ
ঠিক আছে
দুই
কোনো কেবলের সমস্যা কেবলের সমস্যা না হ্যাঁ
ভালো করেছ বন্ধু ঠিকানা না রেখে ভালো করেছ বন্ধু না আসার কোনো কারণ সাজাতে হবে না তোমায় আর বানানো কাহিনী শোনাতে হবে না কথা দিয়ে না রাখার ঠিকানা না রেখে ভালোই করেছ বন্ধু হঠাৎ খেয়ালি দিনে কাছে এসে পথ চিনে হঠাৎ খেয়ালি দিনে কাছে এসে পথ চিনে সুযোগ পাবে না দিয়ে যেতে আর অভিনয় উপহার আশার কোনো কারণ সাজাতে হবে না তোমায় আর বানানো কাহিনী শোনাতে হবে না কথা দিয়ে না রাখার ঠিকানা না রেখে ভালোই করেছ বন্ধু। তোমার হিসাবে কি ভুল রয়েছে নিজেই ধরেছ তুমি। ভুলে যেতে চেয়ে ভালোই করেছ তুমি। তোমার হিসাবে কি ভুল রয়েছে নিজেই ধরেছ তুমি। ভুলে যেতে চেয়ে ভালোই করেছ তুমি। আমার নিয়তি নিয়ে কোনো অভিযোগ দিয়ে আমার নিয়তি নিয়ে কোনো অভিযোগ দিয়ে আমিও পাব না কোনো অবকাশ কোনো কথা জানবার। আমিও পাব না কোনো অবকাশ কোনো কথা জানবার। না আসার কোনো কারণ সাজাতে হবে না তোমায় আর। বানানো কাহিনী শোনাতে হবে না কথা দিয়ে না রাখার। ঠিকানা না রেখে ভালোই করেছ বন্ধু। না আসার কোনো কারণ সাজাতে হবে না তোমায় আর। বানানো কাহিনী শোনাতে হবে না কথা দিয়ে না রাখার। ঠিকানা না রেখে ঠিকানা না রেখে ঠিকানা না রেখে ভালোই করেছ বন্ধু।
Thank you, Ishik, for this beautiful ride of nostalgia. When the world goes silent, the mind grows loud. The next song captures those restless nights filled with memories, longing, and emotions that refuse to sleep. A song that many of us have lived in the quiet hours of night. I now request Ahan Chakraborty to join us.
Hello, hello, hello.
দু চোখে আমার আছো কেন নয়ন জুড়ে ঘুম আসে না ঘুম আসে না
धा सा नी रे नी पा सा नी पा नी धा 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 मा रे नी रे मा मा गा गा सा गा मा मा धा pa ma ba dha pa ma ba dha pa ma ga ma 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 ga ma 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 ga re ga 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 re ga ma ga re re ni ma ba dha pa 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 ni ma re ni dha ba dha ma ga re ga dha sa ga re sa ni dha pa ma ga re sa go ma she na দু চোখে আমার আছো কেন নয়ন জুড়ে ঘুম আসে না ঘুম আসে না ঘুম আসে না দু চোখে আমার আছো কেন নয়ন জুড়ে আমি কেমনে কাটাই কেমনে কাটাই না জানি না আমি কেমনে কাটাই না জানি না ঘুম আসে না আসে না কত কথা ভিড় করে আসে মনে কত কথা ভিড় করে আসে মনে কত ছবি নিধহারা দু নয়নে কত কথা ভিড় করে আসে মনে কত ছবি নিধহারা দু নয়নে স্মৃতি বুকে কেন কাটে সাঁতার স্মৃতির বুকে কেন কাটে সাঁতার এ আঁধারে বলো না এ আঁধারে বলো না ঘুম আসে না দু চোখে আমার আছো কেন নয়ন জুড়ে আমি কেমনে কেমনে কাটাই জানি না ঘুম আসে না ঘুম আসে না ঘুম
unmatched grace. This Rabindra Sangeet is not just a song, but a state of mind, a gentle prayer for stillness and contentment. Now we request Professor Amita Mojumdar to join us on stage. Professor Mojumdar is an alumnus of ISI and was a professor of Economic Research Unit, ISI Kolkata.
কি এটা শোনা যাচ্ছে? বাবা, এই দাঁড়াও, এটা তো ইয়ে করতে পারছি না। এখানটা দাও। হ্যালো, good evening. I'm going to sing a Tagore song. It celebrates soul's liberation, the mind soaring on music, and a deep connection with nature, allowing earthly concerns like piling work to be set aside. এমনি করে যায় যদি দিন যাক না, যাক না, এমনি করে যায় যদি দিন যাক না, মন উড়েছে উড়ুক না রে, মেলে দিয়ে গানের পাখনা, যাক না, এমনি করে যায় যদি দিন যাক না। আজকে আমার প্রাণ ফোয়ারার সুর ছুটেছে, দেহের বাঁধ টুটেছে, আজকে আমার প্রাণ ফোয়ারার সুর ছুটেছে, দেহের বাঁধ মেলেছে আকাশের ওই সুনীল ঢাকনা, যাক না এমনি করে যায় যদি দিন, যাক না। ধরণী আজ মেলেছে তার হৃদয় খানি, সে যেন রে কাহার বাণী। ধরণী আজ মেলেছে তার হৃদয় খানি। কঠিন মাটি মনকে আজি দেয় না বাধা, সে কোন সুরে সাধা। বিশ্ববালে মনের কথা কাজ পড়ে আজ থাকে, থাক না, যাক না এমনি করে যায় যদি দিন, যাক না। মন উড়েছে উড়ুক না রে, মেলে দিয়ে গানের পাখনা, যাক না এমনি করে যায় যদি দিন, যাক না। থ্যাংক ইউ।
Thank you, ma'am, for such a captivating performance. Art does not always soothe. Sometimes it awakens, and poetry has a way of asking difficult questions softly yet firmly. These poems challenge ideas of completeness, authority, and power. কারণ প্রশ্ন করাটা অভদ্রতা নয়, প্রশ্ন করা মানে সচেতনতা। With that, we request Professor Kiranmay Das on stage. Professor Das is an alumnus of ISI and currently a professor of Interdisciplinary Statistical Research Unit, ISI Kolkata.
জীবন সত্যকে তুলে ধরা আমার অতি পছন্দের দুটি কবিতার আমি শোনাবো। আজকে ভারতবর্ষের পরিস্থিতিতে দাঁড়িয়ে এই দুটি কবিতা আমার কাছে খুব প্রাসঙ্গিক মনে হয়। প্রথম কবিতাটি কবি লিখেছিলেন আজ থেকে প্রায় 60-70 বছর আগে, কিন্তু এখনও যখন প্রতিদিন খবরের কাগজ খুলি কবিতাটা বড় জীবন্ত মনে হয়। বিখ্যাত কাহিনী দি নেকেড কিং অবলম্বনে নীরেন্দ্রনাথ চক্রবর্তীর লেখা কবিতা উলঙ্গ রাজা। সবাই দেখছে যে রাজা উলঙ্গ, তবুও সবাই হাততালি দিচ্ছে, সবাই চেঁচিয়ে বলছে সাবাস সাবাস। কারো মনে সংস্কার, কারো ভয়, কেউ বা পরান্নভোজী, কৃপা প্রার্থী, উমেদার, প্রবঞ্চক, কেউ বা নিজের বুদ্ধি অন্য মানুষের কাছে বন্ধক রেখেছে, কেউ ভাবছে রাজবস্ত্র সত্যি অতীব সূক্ষ্ম, চোখে পড়ছে না যদিও তবু আছে, অন্তত থাকাটা কিছু অসম্ভব নয়। গল্পটা সবাই জানে, কিন্তু সেই গল্পের ভেতর শুধু আপাদমস্তক ভীতু ফন্দিবাজ বা নির্বোধ স্তাবকরাই ছিল না, একটি শিশুও ছিল, সাহসী, সরল, সত্যবাদী, নির্ভীক একটি শিশু নেমেছে গল্পের রাজা বাস্তবের প্রকাশ্য রাস্তায়। আবার হাততালি উঠছে মুহুর্মুহু, জমে উঠছে স্তাবক বৃন্দের ভিড়। কিন্তু সেই ছেলেটিকে আমি ভিড়ের মধ্যে আজ কোথাও তো দেখছি না। ছেলেটি কোথায় গেল? কেউ কি তাকে কোনো পাহাড়ের গোপন গুহায় লুকিয়ে রেখেছে, নাকি সে গাছ মাটি পাথর নিয়ে খেলতে খেলতে ঘুমিয়ে পড়েছে কোনো দূর কিংবা কোনো প্রান্তরের গাছের ছায়ায়? যাও, তাকে যেমন করেই হোক খুঁজে আনো। সে একবার এই উলঙ্গ রাজার সামনে নির্ভয়ে দাঁড়াক। সে একবার এই হাততালির ঊর্ধ্বে গলা তুলে জিজ্ঞাসা করুক, রাজা, তোর কাপড় কোথায়? আমার দ্বিতীয় কবিতাটি কবি অংশুমান করের লেখা। কবিতাটির নাম সেই অখণ্ডতা আমি চাই না। যদি অন্ধ্রপ্রদেশের জঙ্গলে জঙ্গলে ছড়িয়ে পড়ে তেলেঙ্গানা নামের এক দাবানল, যদি ব্রহ্মপুত্রের ঔরসে অহমের গর্ভ বিদীর্ণ করে বেরিয়ে এসে বোরোল্যান্ড ঘোষণা করে, পাপ আর গর্ভ হলো ছাই চাপা আগুন, যদি পর্যটক নেই বলে দার্জিলিংয়ে সূর্য না ওঠে 31 দিন, যদি কাশ্মীরে শুকিয়ে যায় ডাল লেক, যদি মেঘালয়, মণিপুর, সমস্ত নর্থ ইস্ট একসঙ্গে বলে ওঠে, কোথায় জন গণ মন সঙ্গীতে আমরা কোথায়, যদি আরেকবার অরুণাচল প্রদেশ বলে ওঠে, চীনের চেয়ারম্যান আমাদের চেয়ারম্যান, যদি মধ্যপ্রদেশের ছোট্ট একটি জেলায় বিন্দুর মতো একটি গ্রাম হঠাৎ একদিন বলে ওঠে, मैं हूं ইন্ডিয়া, যদি ওড়িশার ভেতর জেগে ওঠে আরেকটা ওড়িশা, যদি পাঞ্জাবের ভেতর জেগে ওঠে আরেকটা পাকিস্তান, যদি উত্তরের সঙ্গে দক্ষিণের মুখ দেখা দেখি বন্ধ হয়, যদি ব্যর্থ হয় শচীন, ব্যর্থ হয় শাহরুখ, ব্যর্থ হন রবিশঙ্কর, হেরে যান রবীন্দ্রনাথ, আর শেষ পর্যন্ত এই পোড়া দেশটাকে এক করার জন্যে যদি হতভাগী তোকে নাম পাল্টে সাজতে হয় অভয়া, তবে চাই না সেই অখণ্ডতা, আমি চাই না।
Thank you for such a thought-provoking message. When we remain indifferent to injustice, power begins to silence the powerless. Change is never born out of silence. It rises through resistance. কবি শঙ্খ ঘোষের কথায়, প্রতিবাদের নিভন্ত চুল্লিতে আগুন দিয়ে প্রতিটা মানুষ ছিনিয়ে নিক নিজেদের বেঁচে থাকার অধিকার। Let's again welcome Shreya Chatterjee on stage.
আর একটু কাল বেঁচেই থাকি বাঁচার আনন্দে, নিভন্ত এই চুল্লিতে মা একটু আগুন দে। আর একটু কাল বেঁচেই থাকি বাঁচার আনন্দে, নটন নটন পায়রা গুলি খাঁচাতে বন্দি, দু এক মুঠো ভাত পেলে তা ওড়াতে মন্দি। নটন নটন পায়রা গুলি খাঁচাতে বন্দি, দু এক মুঠো ভাত পেলে তা ওড়াতে মন্দি। হায় তোকে ভাত দি, কি করে যে ভাত দি, হায় হায় তোকে ভাত দেব, কি দিয়ে যে ভাত দেব, হায়। নিভন্ত এই চুল্লি তবে একটু আগুন দে, হাড়ের শিরায় শিখার মাতন মরার আনন্দে। নিভন্ত এই চুল্লি তবে একটু আগুন দে, হাড়ের শিরায় শিখার মাতন মরার আনন্দে। দুই পারে দুই রুই কাতলার মারনি ফন্দি, বাঁচার আশায় হাত হাতিয়ার মৃত্যুতে মন্দি। তোর কিনা জমকে কে সামলায়, ধার চকে চকে থাবা ওই দেখছো না হামলায়, আরে যাসনে ও হামলায় যাসনে। কান্না কন্যার মায়ের ধমনীতে আকুল ঢেউ তোলে জলে না, মায়ের কান্নায় মেয়ের রক্তের উষ্ণ হাহাকার মরে না। চললো মেয়ে রানে চললো, রনে চললো, চললো মেয়ে রানে চললো, রনে চললো। বাজে না ডম্বরু অস্ত্র ঝনঝন করে না, জানলো না কেউ। চললো মেয়ে রানে চললো, রনে চললো, চললো মেয়ে রানে চললো, রনে চললো। পেশির দৃঢ় ব্যথা, মুঠোর দৃঢ় কথা, চোখের দৃঢ় জ্বালা সঙ্গে নিয়ে চললো মেয়ে রানে চললো, রনে চললো, চললো মেয়ে রানে চললো, রনে চললো। তোর মৃত্যু এলো, মৃত্যুর গান গা, মায়ের চোখে বাপের চোখে দু তিনটে গঙ্গা। ইকড়ে অজর মৃত্যু এলো, মৃত্যুর গান গা, মায়ের চোখে বাপের চোখে দু তিনটে গঙ্গা। দুর্বাতে তার রক্ত লেগে সহস্র সঙ্গী, জাগে ধক ধক যজ্ঞে ঢালে সহস্র মন ঘি। যমুনাবতী সরস্বতী কাল যমুনার বিয়ে, যমুনা তার বাসর রচে বারুদ বুকে দিয়ে, বিষের টোপর নিয়ে। যমুনাবতী সরস্বতী গেছে এ পথ দিয়ে, দিয়েছে পথ গিয়ে। যমুনাবতী সরস্বতী গেছে এ পথ দিয়ে, দিয়েছে পথ গিয়ে। নিভন্ত এই চুল্লিতে বন আগুন ফলেছে, অবন আগুন ফলেছে, অবন আগুন ফলেছে।
What an expressionful performance. Some emotions feel like a restless wind, free, unpredictable, and impossible to hold on to. The next song speaks of wandering hearts, quit longing, and the strange comfort of losing oneself along the way. A melody that drifts between freedom and yearning. Let's now invite Professor Arijit Chakraborty, who is an alumnus of ISI and currently a faculty of Applied Statistics Unit, ISI Kolkata.
Hello. So, good evening, everybody. This is the birth centenary year of the great composer Sholil Chowdhury, and actually, singer Jyotileshwar Mukhopadhyay's birthday was just 2 days back. So this is my homage to these great individuals. So I'm trying and not lot of practice of songs, but I'm trying. Okay. So this song was written and composed by Sholil Chowdhury and recorded by Jyotileshwar Mukhopadhyay in 1968, and later it was recorded by Subir Sen, Pagol Hava. পাগল হাওয়া পাগল হাওয়া কি আমার মতন তুমিও হারিয়ে গেলে ফুলের বনে হাজারো রঙের মেলায় সুরভি লুটের খেলায় তারে নাহি পেলে পাগল হাওয়া কি আমার মতন তুমিও হারিয়ে গেলে ফুলের বনে হাজারো রঙের মেলায় সুরভি লুটের খেলায় তারে নাহি পেলে পাগল হাওয়া বসন্ত যখন এসে ডেকে যায় আমারে কি জানি কি বা রূপে সে আসে চুপে চুপে জড়াতে চায় আমারে বসন্ত যখন এসে ডেকে যায় আমারে কি জানি কি বা রূপে সে আসে চুপে চুপে জড়াতে চায় আমারে বসন্ত যখন বনে বনে তখন বাতাসে মাতালি বাসিতে কি কথা যায় বলে পাগল হাওয়া কি আমার মতন তুমিও হারিয়ে গেলে ফুলের বনে হাজারো রঙের মেলায় সুরভি লুটের খেলায় তারে নাই পেলে পাগল হাওয়া এবার সাঙ্গমোর হয়েছে খেলা গো বিজয়িনী ঝরা ফুলে পল্লবে সে মালা গাথো তবে পরায় দাও বিজয়িনী এবার সাঙ্গমোর হয়েছে খেলা বিজয়িনী ঝরা ফুলে পল্লবে সে মালা গাথো তবে পরায় দাও বিজয়িনী এবার সাঙ্গমোর হার মানা হারে আমারে সে বাঁধন সাজায় সজনি সে বাঁধন দাও গলে পাগল হাওয়া কি আমার মতন তুমিও হারিয়ে গেলে ফুলের বনে হাজারো রঙের মেলায় সুরভি লুটের খেলায় তারে নাহি পেলে পাগল হাওয়া। থ্যাংক ইউ।
What a lovely performance, sir. The next performance moves between overflowing passion and gentle restraint, where emotions speak both boldly and softly, two moods, two languages, yet one shared heartbeat. May I now request Mrs. Monali Mitra Paladi on stage, who is an alumnus of ISI and currently is the Deputy Librarian of ISI Kolkata. She will be accompanied by Bodhuja Bhattacharya. to emotion, and emotion in turn breathes life into melody. What begins in calm discipline slowly opens into devotion and surrender. This performance takes us on a journey from stillness to longing, from structure to the heart's unspoken question. Let's now welcome Prognodipta Mojumdar on stage. He will be accompanied by Shevanti Bashu and Bodhuja Bhattacharya.
Hello. এতেই হয়ে যাবে
Hello, hello.
मन सुख पावे अतमन सुख पावे अतमन सुख पाए साजन मोरे घर आए मंगल गा पुरावो मंगल गावो चौख पुरावो प्रेम पिया हम पाए प्रेम पिया हम पाए साजन मोरे घर आए re
pa ga ga ma ga sa ma ga ma ga sa ni pa ma ga.
তোমাকে ভালোবেসে কোথায় যাব শেষে জানি না সেই দেশে চিরাগো আছে কি না তবে সে আন্ধারে নিষাদে গান্ধারে কে তাকে প্রাণধারে প্রেয়সী তোমা বিনা যদি বা প্রাণ যায় যেন না গান যায় হৃদয় জান যায় তাকে তো রাখা যায় না
তোমাকে ভালোবেসে কোথায় যাব শেষে জানি না সেই দেশে চিরাগো আছে কিনা তবে সে আন্ধারে নিখাদে গান্ধারে কে তাকে প্রাণধারে প্রেয়সী তোমা বিনা
যদি বা প্রাণ যায় যেন না গান যায় হৃদয় জান যায় তাকে তো রাখা যায় না গমা পানিয়ে সা জানে মন স্পর্শ সঙ্গোপন যেখানে ছো তাকে ভাঙবে তমসাকে এমনই সমন সেই মনেরই নাম জানলে পাল্টাতাম নীরবে সংযোগে রেখেছি মনোযোগে দিইনি কিছুই দাম তোমাকে ভালোবেসে কোথায় যাব শেষে জানি না সেই দেশে চিরাগো আছে কিনা তবে সে আন্ধারে নিখাদে গান্ধারে কে তাকে প্রাণধারে প্রেয়সী তোমা বিনা যদি বা প্রাণ যায় যেন না গান যায় হৃদয় জান যায় তাকে তো রাখা যায় না তোমাকে ভালোবেসে কোথায় যাব শেষে জানি না সেই দেশে চিরাগো আছে কিনা
Thank you, Prognitha and group, for such a mesmerizing performance. Some melodies refuse to stay within one language because emotions have no borders. This mashup brings together two timeless reflections, one that whispers of tender longing and another that questions life, love, and direction. As Bengali nostalgia meets Hindi introspection, memory and meaning flow together in one musical breed. Let's now welcome Srijan and Shebhunti on stage, and they will be accompanied by Boidurjo. Thank you.
Hello. Hello, hello. Hello, hello.
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 আমায় প্রশ্ন করে নীল ধ্রুব তারা আর কত কাল আমি রব দিশাহারা
রব দিশাহারা জবাব কিছুই তার দিতে পারি নাই শুধু পথ খোঁজে কেটে গেল এ জীবন সারা এ জীবন সারা কहीं दूर जब दिन ढल जाए साँझ के दुल्हन बदन चुराए चुप कैसे आए
मेरे ख्यालों के आंगन में कोई सपनों के दीप जलाए दीप जलाए
कहीं दूर जब दिन ढल जाए साँझ के दुल्हन बदन चुराए चुप कैसे आए আমি পথ খুঁজি না কো পথ মোরে খোঁজে মনো যা বুঝে না বুঝে না বুঝে তা বোঝে
कहीं तो ये दिल कभी मिल नहीं पाते कहीं पे निकल आए जन्म के नाते
আমার চতুর পাশে সব কিছু যায় আসে আমি শুধু তুষারিত গতিহীন ধারা গতিহীন ধারা कहीं दूर जब दिन ढल जाए साँझ की दुल्हन बदन चुराए चुप कैसे आए न जाओ सैया चुरा के बैया कसम तुम्हारी मैं रो परूंगा मचल रहा है सुहाग मेरा जो तुम न होंगे तो क्या करूंगा क्या करूंगा
ফুলেরও কথা শুনে বকুল হাসে কই তাহার মতো তুমি আমার কথা শুনে হাসো না তো ধরার ধুলিতে যে ফাগুন আসে কই তাহার মতো তুমি আমার কাছে কবু আসো না তো
চাঁদের আলোয় রাত যায় যে ভোরে তাহার মতো তুমি করো না কেন ওগো ধন্য মোরে
চাঁদের আলোয় রাত যায় যে ভোরে তাহার মতো তুমি করো না কেন ওগো ধন্য মরে
जो मुझसे आँखिया चुरा रहे हो तो मेरी इतनी अर्ज भी सुन लो
যেমন করে নিরে একটি পাখি শাখিরে কাছে তার নেয় গুণাকে যেমন করে সে ভালোবাসে
কই তাহার মতো তুমি আমায় তবুও ভালো বাসো না তো न जाओ सैया चुरा के बैया कसम तुम्हारी मैं रो परूंगा मचल रहा है सुहाग मेरा जो तुम न होंगे तो क्या करूंगा क्या करूंगा
Not all love needs grand declarations. Sometimes it is the moon, the rain, and the silence in between that feels most beautiful. The next song reminds us how simplicity becomes magical when the heart is content. A timeless song that feels like a warm memory, soft and comforting. Let's now welcome Srijan Chattopadhyay and Renika Jana on stage. They will be accompanied by Boidurcho Bhattacharya.
बड़े अच्छे लगते हैं
क्या
ये धरती ये नदियाँ ये रहना और तुम बड़े अच्छे लगते हैं ये धरती ये नदियाँ ये रहना और तुम ओ माझी रे जाइयो पिया के देश हम तुम कितने पास है कितने दूर है चांद सितारे सच पूछो तो मन को झूठे लगते हैं ये सारे हम तुम कितने पास है कितने दूर है चांद सितारे सच पूछो तो मन को झूठे लगते हैं ये सारे मगर सच्चे लगते हैं ये धरती ये नदियाँ ये रहना और तुम तुम इन सबको छोड़ के कैसे कल सुबह जाओगी मेरे साथ इन्हें भी तो तुम याद बहुत आओगी तुम बिन सबको छोड़ के कैसे कल सुबह जाओगी मेरे साथ इन्हें भी तो तुम याद बहुत आओगी बड़े अच्छे लगते हैं ये धरती ये नदियाँ ये रहना और तुम बड़े अच्छे लगते हैं
Thank you, friends, for such sweetness. As the evening gets old, we return to memories that bind us all. This song is not just about the past, it is about shared laughter, friendships, and moments that continue to live within us. Let us end this journey together in one voice, one emotion. Let's now have a chorus of all. I would request whoever is not on the stage, please come forward so that we can have this moment together.
প্রাণের মাঝে আয় মোরা সুখের দুঃখের কথা কব প্রাণ জুড়াবে তার পুরানো সেই দিনের কথা ভুলবে কি রে হায় ও সেই চোখের দেখা প্রাণের কথা সে কি ভোলা যায় মোরা ভোরের বেলা ফুল তুলেছি তুলেছি দোলা বাজিয়ে বাঁশি গান গেয়েছি বকুলের তলায় মোরা ভোরের বেলা ফুল তুলেছি তুলেছি দোলা বাজিয়ে বাঁশি গান গেয়েছি বকুলের তলায় হায় মাঝে হলো ছাড়া ছাড়ি গেলেম কে কোথায় আবার দেখা যদি হলো সখা প্রাণের মাঝে আয় পুরানো সেই দিনের কথা ভুলবে কি রে হায় ও সেই চোখের দেখা প্রাণের কথা সে কি ভোলা যায় সে কি ভোলা যায় সে কি ভোলা
Thank you to all the performers, the organizers, and also my dear audience for being with us in this evening. I hope you enjoy your holidays. Wishing you a Merry Christmas and a Happy New Year.